When we talked about relations, we mentioned there were certain types of relations that we were going to consider, and the one that we look at now is what's called an equivalence relation. When R is a relation from a set A to itself, notice that this now has the same set in both spots here for the product set. Okay? If there are three additional properties that are satisfied, we're going to call it an equivalence relation. The first is called the reflexive property. Everything in the set is related to itself. This might not happen. I could certainly build a product set A cross A, then take a certain subset and not include every single ordered pair of the form A comma A. If I include every ordered pair of the form A comma A, it's called reflexive. If any time A is related to B, that automatically implies B is related to A, that's called the symmetric property. If A is related to B, then B is related to A. Any ordered pair that appears in one order must appear in the other as well. And the third property is the transitive property. Given any three elements of the set, if A is related to B and B is related to C, that will imply that A is related to C. So any chain of successive relations can be shortened. Okay, once you have this property, you can do it in many, many steps. If A is related to B and B is related to C and C is related to D and D is related to E, well then A is related to E overall. If a relation has all three of these properties, the reflexive property, the symmetric property, the transitive property, then we call it an equivalence relation on A. Note, in all three of these, it's crucial that the left and right elements are coming from the same set. So here we have something and itself on both sides of the relation. In other words, the ordered pair has to be drawing from the same set in both spots. Here, A appears on the left and on the right, B appears on the right and on the left. So A and B both had to be coming from the same set in order for this to make any sense. And finally here again, B appears on the right and left. So that requires that both the left and right side that we're using for our original product set had to be the same set. So all of these only make sense if we have relations from a set to itself. If we have relations from a set to a different set, none of these definitions even make sense. Let's look at an example. So because both sets have to be the same set, we frequently just say a relation on R. And what we mean is a relation between R and itself. So here's a relation that is reflexive and symmetric, but is not transitive. A is related to B if the product is bigger than or equal to 0. Why is it reflexive? That's claiming that every element of the real numbers is related to itself. Okay, this is a universally quantified statement. Every element of the reals is related to itself, so pick an element of the reals without making any specific assumptions on it. Well then, the product A times A is just A squared, and square numbers are always bigger than or equal to 0. So what have we shown? An arbitrary real number satisfies A times A is bigger than or equal to 0. An arbitrary real number is related to itself, and this is the reflexive property. Next up, is this a symmetric property? So this is a conditional statement. If A is related to B, then B is related to A. So how do I prove that? We get to assume the hypothesis, A is related to B. Our relation says A is related to B exactly when the product of the two numbers is bigger than or equal to 0. So we get to assume that A times B is bigger than or equal to 0. Of course, this implies B times A is bigger than or equal to 0, which means B is related to A. B is related to A means left number times right number is bigger than or equal to 0. Left number times right number is bigger than or equal to 0, so B is related to A. We assumed A was related to B. We derived B was related to A. That is the conditional statement that underlies the definition of a relation being symmetric. And finally, transitive. A relation being transitive is also a conditional statement, and it has two hypotheses. We get to assume A is related to B and B is related to C. And then we would try to derive that A is related to C, but this is not transitive. So we get to just generate a counterexample. Remember, all of these are universally quantified, so if they're true, you have to prove they're always true. If they're false, you just have to prove it false once. So here's an example of a choice of A and B and C. where A is related to B and B is related to C. A times B is bigger than or equal to 0. B times C is bigger than or equal to 0. So A is related to B and B is related to C. Both hypotheses are satisfied. But the conclusion is not, because A times C is not bigger than or equal to 0. So it's possible to pick a certain A, B, and C that violated A related to B and B related to C implies A related to C. We generated a counterexample to the definition of a relation being transitive, and therefore it's not transitive. So we have here a relation that is reflexive and symmetric, but not transitive. So it's not an equivalence relation because it does not have all three. Another example, another relation on R, this one is going to be reflexive and transitive, but not symmetric. A is related to B if A is less than or equal to B. Is it reflexive? So since this is reflexive and we have to prove it, we pick an arbitrary real number, and now we need to show that it is related to itself. A is certainly equal to A, which means A is less than or equal to A, which means A is related to A because that's what our relation is. One number is related to the second if the first is less than or equal to the second. If I put the same number here, I get a true statement, so A is always related to itself. That means it is a reflexive relation. However, this is not symmetric. So in order to show that a relation is not symmetric, we merely need to find one counterexample. We need to find an example of A and B where A is related to B, but B is not related to A. Here's a possible choice, 0 and 1. 0 is less than or equal to 1, true, so A is related to B. But 1 is not less than or equal to 0, so B is not related to A. So since we were able to find one example where symmetry fails, it is not symmetric overall. Transitive, this is transitive. Remember that transitive is a conditional statement, so to prove that it is transitive, we're going to assume the hypotheses. Assume A is related to B and also B is related to C. So A is less than or equal to B, and B is less than or equal to C. Now the inequality sign has this transitive property. If A is less than or equal to B and B is less than or equal to C, well then A is less than or equal to C. So basically, because we used something we already knew to be transitive, yes, this is a transitive relation. Assuming A was less than or equal to B and B was less than or equal to C, that is, assuming A is related to B and B is related to C, we derived A is less than or equal to C. In other words, A is related to C. So that's the definition of being transitive, and we proved it the same way we do any other conditional statement. We assumed the hypotheses and we derived the conclusion. Another example, here's a relation that is transitive and symmetric, but not reflexive. A is related to B if the product of the two numbers is not 0. Well, if it's not reflexive, we just need to find one counterexample. Can I find one number that fails this test, that A times itself is equal to 0? Absolutely. If we let A equal 0, then A times itself is 0, meaning it is not related to itself. Now this happens to be the only choice of number that is not related to itself by this relation, but that's fine, okay? To be reflexive, everything must be related to itself. Okay, anything else I picked, if I did A times A, I wouldn't get out 0. But there is one particular number for which this fails, so this is not a reflexive relation. What about symmetry? Well, it's a conditional statement, so go ahead and assume that A is related to B, that is, the product is not 0. Well then, B times A is also not 0, because I don't know what number it is, but it's the same as A times B, and that wasn't 0. So since B times A isn't 0, B is related to A. Assuming A is related to B, we quickly got B is related to A. That's the definition of symmetry. Finally, transitive. Let's assume A is related to B and B is related to C. So A times B is not 0 and B times C is not 0. So none of the three numbers were 0 to begin with. Okay? If A were 0, then A times B would have been 0. Similarly, if B were 0, A times B and B times C would have been 0. And if C was 0, then B times C would have been 0. So none of these three numbers were 0 to begin with. So since A and C are both non-zero numbers, when I multiply them, I don't get out 0. That is to say, A is related to C. So having assumed that A is related to B and B is related to C, we were able to derive that A is related to C. And that's transitivity. Okay, if you actually think about this relation, two numbers are related exactly when neither one of them is 0. So what ordered pairs go into this relation? All ordered pairs where neither term is 0. And this does turn out to be symmetric and transitive, okay? If none of the two numbers are 0, it doesn't matter which you put on the left versus the right. If I have two separate pairs where none of these are 0 and none of these are 0, well then neither of these was 0. However, it is possible to try to form a pair A, A of 0, 0, which would fail, so it's not reflexive. So having discussed a few things that are not equivalence relations, let's talk about something that is. Another relation on R, A is related to B if A squared equals B squared. Is this reflexive? So pick any real number. A squared certainly equals A squared, so yes, A is related to itself. If I put the same number on the left and right, this is true. So the same number on the left and right, they are related. So it is a reflexive relation. Is it symmetric? First off, assume A is related to B, so A squared equals B squared. Then yes, B squared equals A squared, in other words, B is related to A, so we are symmetric. Is it transitive? Well, if I assume A is related to B and B is related to C, then A squared equals B squared and B squared equals C squared, so A squared equals C squared because the equal sign is transitive, and therefore A is related to C. So R is in fact transitive. So it was reflexive, it was symmetric, it was transitive. It's an equivalence relation. Okay, the equals sign has all these properties. We mentioned it back when we were discussing set theory, that any set is equal to itself, and the equality sign is also symmetric and transitive. And this holds for numbers and things like equations as well. The equals sign carries these properties. So if you define a relation in terms of something involving an equal sign, you will most frequently get out an equivalence relation. I wouldn't call that a hard and fast rule, but as a rule of thumb, the equal sign has these properties, so it tends to carry through. So if R is an equivalence relation on A, so we have an equivalence relation, we have symmetry, reflexivity, and transitivity, we can define what's called the equivalence class of that element. It's square brackets around A, and it's everything in the set that is related to it. Okay, so the equivalence class of A, you can only talk about it if R is already known to be an equivalence relation. It's the set of all elements which are related to A. Because equivalence relations are reflexive, A is always related to itself, so A belongs to its own equivalence class. What belongs to an equivalence class? Things that are related to it. A is related to itself because we are reflexive. Symmetry of equivalence relations tells me if B is related to A, in other words, B is in the equivalence class of A, then A is related to B, in other words, A is in the equivalence class of B. So elements are always in their own equivalence classes, and if something is in the equivalence class of another, then I could switch them for free. And that comes from reflexivity and symmetry, respectively. Now we're going to discuss how equivalence classes create what are called partitions. Okay, a partition of a set is merely a collection of subsets whose union is the entire thing, but any two subsets that we have in this collection do not intersect at all. So they are a collection of sets that are disjoint, their intersections are empty, but if I union them, I get back the entire set. That's a partition. Theorem 1. Suppose we have an equivalence relation on A. A and C are two elements of A. And here, the equivalence class of A, which is everything related to it by R, intersect the everything related to C by R, is not empty. Then those two sets were actually equal. So before we actually start the proof of the assertion that these two sets are equal, we're going to understand what this given actually tells us. So assume the equivalence class of A intersect the equivalence class of C is not empty. Well, if it's not empty, there is something in it, and if this is an intersection that has an element, then there has to be something that's in both. Now, all of this is existential. There exists an element in both the equivalence class of A and the equivalence class of C. So if we instantiate that, we have to use a new letter. Let's call it B. So there is some element B that is in the equivalence class of A and also in the equivalence class of C. In other words, it's related to both A and C by the equivalence relation R. But R is symmetric, so if B is related to A, then A is related to B. And R is transitive, so if A is related to B and B is related to C, well then A is related to C. I would also point out that since R is symmetric, if A is related to C, then C is also related to A. Now let's get on to showing that these two sets are equal. How do we show two sets are equal? We do it through mutual containment. So first, let's show the equivalence class of A is a subset of the equivalence class of C. How do I show one thing as a subset of another? It's a conditional statement and it has a hypothesis. So let's assume that I have an element of the left set, the equivalence class of A. Our goal now is to show that X belongs to the equivalence class of C. But if X is in the equivalence class of A, it's related to A. So X is related to A and A is related to C. Therefore, X is related to C because we assumed R is an equivalence relation and therefore transitive. But if X is related to C, it's in the equivalence class of C. So any element in the equivalence class of A must be in the equivalence class of C. We have shown that this set is a subset of that one. But we can basically go the other way, okay, in the same way. Let's assume X is related to C. Since C is related to A, by transitivity, X would be related to A, and therefore X is in the equivalence class of A. So you can prove this containment using essentially the same steps in reverse. Since A, the equivalence class of A, is a subset of the equivalence class of C, and the equivalence class of C is a subset of the equivalence class of A, those sets are equal. Okay, Theorem 2. If you have an equivalence relation, and you look at the equivalence classes, you've made a partition. Okay, now just remember, I gave you the definition at the beginning of this slide. A partition of a set is a collection of subsets whose union is the entire set, but also they're all disjoint from one another. So if I take two elements from this collection, their intersection is empty. So that's what we want to show, that if you have an equivalence relation and you look at all the equivalence classes, you've made a partition. So every element of the original set A belongs to its own equivalence class. We discussed this on the previous slide. So if I union all the equivalence classes, I have actually unioned every element of the set, and I've got the original set back through union. But what we've shown here is that two equivalence classes, if they intersect at all, then they were in fact the same set. So by throwing out duplicates, okay, the equivalence classes that remain are all disjoint from one another. Next theorem, anytime you have a partition, that actually defines an equivalence relation. So suppose you take a set A and you chop it up into pieces. Part 1, part 2, part 3, part 4. I've made a partition. If I union these pieces back up, I get the entire original set, but the pieces I chopped up are all disjoint from one another. I have now defined an equivalence relation. So if you have a collection of disjoint sets whose union is the entire thing, you can make a relation by saying two elements of the original set are related if they're in the same piece of the partition. So if I have two elements that are both in piece 1, I say they're related. If I have two elements both in piece 3, I say they're related. But if I have an element from piece 1 and an element from piece 2, they're not related. So this is reflexive because every element of the original set is in the same chunk as itself. So it's related to itself. If two elements are both in the same piece, it doesn't matter which one I consider to be left versus right, so you get symmetry. And you also get transitivity. If A and B are related, then they were in the same chunk. If B and C are related, they were in the same chunk. Therefore, A and C will be in the same chunk. So that is reflexive, symmetric, and transitive. So any way you chop a set into pieces and define a relation by saying two elements are related if they're in the same piece, you have now made an equivalence relation. The purpose of this is just to say equivalence relations are the same thing as partitions. Anytime you have an equivalence relation, you get a partition through equivalence classes. But anytime you make a partition however you want, you've actually made an equivalence relation where the equivalence classes are the pieces of the partition. So partitions of sets and equivalence relations on sets in some fundamental way represent the same thing. Of course, we interpret them very differently. Equivalence relations tend to be interpreted by us as humans as something that relate numbers to each other or elements of set to each other, whereas partitions we understand much more visually as just like chopping things up into pieces. The interesting thing is that from a logical perspective, they both accomplish the same task. So let's take a look at an example. Suppose I have a function. Okay, we're going to begin with a function. It takes an integer and spits out another integer, where f of an integer is the largest multiple of 3 which isn't bigger than x. So for example, what's the largest multiple of 3 not bigger than 10? 9. What's the largest multiple of 3 not bigger than 21? 21 is not bigger than 21. What's the largest multiple of largest multiple of 3 not bigger than -1? It's not actually 0, because 0 is bigger than -1. It's -3. So now let's define a relation. Two elements are related if f of x equals f of y. Now, since we've used an equality sign in defining this relation, things are going to happen pretty quickly. Okay. It's definitely an equivalence relation. If I pick the same number in both spots here, is f of x equal to f of x? Sure it is. If f of x equals f of y, does f of y equal f of x? Yes, so I get symmetry. If f of x equals f of y and f of y equals f of z, is f of x equal to f of z? Yeah, the equality sign is transitive, so I get transitivity. Okay, so we very quickly get that this is an equivalence relation. Two integers are related if the largest multiple of 3 not bigger than x is equal to the largest multiple of 3 not bigger than y. But what are the equivalence classes? What I have to do is take the set integers and partition it somehow into pieces according to equivalence classes. What's the equivalence class of 10, for example? Every integer so that f of x equals f of 10. We already discussed up here that the largest multiple of 3 not bigger than 10 is 9. So what are all the integers whose largest multiple of 3 not bigger than that is 9? It's 9, 10, and 11. The largest multiple of 3 not bigger than 9 is 9. The largest multiple of 3 not bigger than 10 is 9. The largest multiple of 3 not bigger than 11 is 9. But once I hit 12, I'll have bigger multiples of 3, and once I hit 8, I'll have smaller multiples of 3. What's the equivalence class of -1? All integers so that the largest multiple of 3 not bigger than our integer is the same as when I do it to -1. We already discussed the largest multiple of 3 not bigger than -1 is -3. So what are all the integers that satisfy this property? It's -3, -2, and -1. Any one of these numbers, the largest multiple of 3 not bigger than it would be -3. If I start counting up and I hit 0, well, the largest multiple of 3 not bigger than 0 is 0 itself, not the same thing, not -3. If I go down to -4, the largest multiple of 3 not bigger than -4 would be -6, not -3. So these are the three numbers and the only three numbers so that f of x equals -3. What this does is it splits the integers into sets of 3 elements each. Okay? So this happens to be the same thing as the equivalence class of 9 and is the same thing as the equivalence class of 11. This is the same as the equivalence class of -2 and the same as the equivalence class of -3. If I have the integers, okay, so I've got like ... and then I have maybe -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so forth. Okay, here is an equivalence class. Here is an equivalence class. Here's an equivalence class. Here's an equivalence class. Here, and so forth. Okay. The equivalence classes are the set of elements on which the function that we defined up here takes the same value. On this trio of numbers, the function takes the value -6. On this trio of numbers, it takes the value -3. Here it takes value 0. Here it takes the value 3. Here it takes the value 6, and so forth. Okay, so what we have done is we've taken the entire line of infinitely many integers, partitioned it into pieces. They happen to all have 3 elements, but they never overlap, and they will eventually account for all of them. So the equivalence classes under this relation have partitioned the integers into pieces.